Okay, so in 2.3, we're going to learn about biconditionals and definitions. And biconditionals are a new type of statement that help us recognize good definitions. So a biconditional statement combines the conditional statement and its converse, the conditional statement and its converse, as this statement. And you read this statement as P if and only if Q. That means this statement is true for the conditional and the converse. So the biconditional that I give in this box below says a ray is an angle bisector if and only if it divides an angle into two congruent angles. So an angle bisector is a definition we talked about in the last chapter. An angle bisector divides an angle into two congruent angles, two angles of equal measure. It cuts that angle in half. That is a good definition of an angle bisector. Most good definitions should be one sentence. That's what biconditionals do. They help us find out what a good definition is. So in example 1, we're going to get some practice writing a biconditional. So it asks, what is the converse of the following true conditional statement? If the converse is also true, rewrite the statement as a biconditional. So in this statement, it says if two angles have equal measure, then the angles are congruent. So to identify hypothesis and conclusion, two angles have equal measure is the hypothesis. The angles are congruent is the conclusion. So, hypothesis, two angles have equal measure. Conclusion, the angles are congruent. Sorry, I'll do better at my handwriting here. The angles are congruent. So, we're going to circle the converse of these three from these three statements. So remember the converse from last lesson. It swaps the hypothesis and the conclusion. So, if two angles do not have equal measure, this is not going to be it because it negates a statement. The converse does not negate any statements. If two angles are congruent, then the angles have equal measure. That is our winner. It swaps the hypothesis and conclusion. It does not negate anything. Statement 3 negates. That is not what the converse does. The converse is also true, so we write this as a biconditional. We start with the hypothesis. If, or we don't have to use if, sorry, in a biconditional because we have if and only if. So to write this as a biconditional, I just write the hypothesis. And that is two angles have equal measure. I don't use the word if. I ran out of room a little bit there, but two angles have equal measure. If and only if, then I write the conclusion. The conclusion is the angles are congruent. So that is our biconditional. It has if and only if. It doesn't have this traditional if-then form that we have been talking about the last few lessons, but it uses your idea of hypothesis and conclusion to write that biconditional. So, for example 2, it's asking you to identify the conditionals in a biconditional. So this says two numbers are reciprocals if and only if their product is 1. So I'm going to underline hypothesis and conclusion here. The hypothesis of this statement would be two numbers are reciprocals. Okay? So two numbers are reciprocals. So 2/3 and 3/2 are reciprocals. That's an example of reciprocals. 3/4 and 4/3. The conclusion, their product is 1. So literally copying those statements from the original statement. So it asks you to write the conditional and then write the converse. So the conditional is if two numbers are reciprocals, I'm just going to write the number 2 to save me some space. Two numbers are reciprocals, then their product is 1. So just converting it to if-then form. And then, like we covered last lesson, to write the converse of that, I'm just going to start with if two numbers have I'm going to change it. I'm not just going to say if their product is 1. I'm going to say if two numbers have a product of 1. So I'm changing the statement just a little bit, but that doesn't change the truth value of it. If two numbers have a product of 1, then they are reciprocals. So what I would say is this is a good definition because the conditional and the converse are both true. So this biconditional is a good definition. And we'll talk about good definitions a little bit more in the future. So moving to example 3, writing a definition as a biconditional, I'm going to ask you the question, is this definition of a straight angle reversible? Meaning, is the converse also true? If that is true, then we write it as a true biconditional. So it says a straight angle is an angle that measures 180 degrees. So reversible means that if we reverse P the hypothesis and Q the conclusion, it's still true. So the conditional to this, the hypothesis is an angle is a straight angle. Okay? So we write the conditional if an angle is a straight angle. Okay? If an angle is a straight angle, then it measures 180. Okay? So that's the conditional. Hypothesis is an angle is a straight angle. Conclusion, the angle is 180, or it measures 180. To write the converse, I would say if an angle measures 180, if an angle measures 180, then it is a straight angle. So, by the definition of straight angles, I would say that this is reversible. It is true both in the conditional and the converse. So to write the biconditional, all I do is I just write the hypothesis, followed by if and only if, and then I write the conclusion. So I would say an angle is a straight angle if and only if it measures 180. So that's why we spent the last lesson learning about converse, inverse, contrapositive, because this helps us build definitions and understand when a definition is good and when it is not a good definition. So example 4 will be our last example. And in this example, we identify good definitions, which I think is an important thing to practice and to learn. So it asks, is the following statement a good definition? A square is a figure with 4 right angles. So my hypothesis of this is a figure is a square. A figure is a square. My conclusion is it has 4 right angles. So the conditional is conditional statement is if a figure is a square, then it has 4 right angles. All right? So that's my conditional. The converse is I switch hypothesis and conclusion. So my converse of this statement would be if a figure has 4 right angles, then it is a square. So evaluating these, the truth value of these, the conditional statement, if a figure is a square, then it has 4 right angles. That is true. A square has 4 right angles. However, the converse, if a figure has 4 right angles, then it is a square. That is actually false because there are other figures with 4 right angles that are not squares. Okay? So, which statement is true? The conditional, the converse, or both? only the conditional. Only the conditional is true. So the fact that only the conditional is true, this is not a good definition. Is the definition of a square a good definition? No, not this definition. And the reason this definition is not true, or is not a good definition, is the converse is not true. So for a statement to be a good definition, the hypothesis and conclusion, when you swap them, they have to be true both times. So the conditional and the converse have to both be true. If both conditional and converse are true, this would be a good definition. So the reason it's not a good definition is because the converse is false. So you're ready to move on. You're going to practice this. Yes, you will have to write a little bit more. Once we're finished with this, you're going to do the checkpoint. You're going to do the practice first, then the checkpoint. Next class, we are going to review for our quiz, our first quiz of Chapter 2, and then we're going to take that quiz. So next class, we're going to review and take our next quiz.